Let's add a little bit of more details to the ocean story about intraseasonal variability, and this is looking at TMI microwave imager data for August 1st, 1998, which was a strong La Nina by then. So the cold sea surface temperatures here in the cold tongue are much colder than normal, but you see these kind of wavy patterns here, and also in this region and in the Somali Current region here. So these are the instabilities we mentioned before, but the point is that these are sometimes the barotropic instability created between the eastward equatorial undercurrent here and the westward north equatorial current to the north, and here is the low latitude jet and the boundary current that begins to experience instabilities because of this sloping coastline, and here there are instabilities between again different types of currents, and the SST fronts makes it much more visible, and you also have instability waves here. So that those can be also captured by simply looking at intraseasonal SST anomalies by temporal filtering between 20 and 100 days, which is typically what we do for MJOs in the atmosphere and the mesos in the atmosphere and so on. So you can see that that kind of spatial instability structures are captured at all these places here. But you can then split that into zonal bandpass filtering or spatial smoothing using a box of 12 degree by 12 degree, which extracts the large scale organized intraseasonal SST anomalies. So you can think of it as the residual effect or the rectification effect of this high spatial variability, leaving behind warmer sea surface temperatures because of instability waves. And here similarly you got rectified signals, and here is the small scale residual of that shown here by the difference between this and this. So you can see that the intraseasonal variability in the ocean can be created internally, not always related to surface forcing by MJOs and mesos. And then the question is, how do these intraseasonally, internally generated sea surface temperature anomalies affect coupled dynamics? It turns out, for example, that there is enough modulation of mean sea surface temperatures here that the east-west sea surface temperature gradient can be modulated, and that leads to pressure response in the atmosphere, wind response, and you can get east-west variabilities that are often of the same order of magnitude as an El Nino anomaly, a weak El Nino anomaly. And there are even modeling studies that have argued that tropical instability waves, which are what these are called, can in fact trigger El Ninos with these kind of processes. So that's something to keep in mind in terms of the other side of the story, where atmospheric internal variability projecting onto intraseasonal timescales as MJOs and mesos may be coupled and influencing internal dynamics of the ocean, but internal dynamics of the ocean has the potential to affect atmospheric dynamics and coupled dynamics as well. Simply looking at intraseasonal variability of sea surface temperatures at a small scale, so less than 10 degree in longitude and latitude, so that's order 1,000 kilometers. This is obtained by computing the 0.25 by 0.25 degree region, the temporal standard deviation among ensembles of residual fields shown in the previous figure. So this is showing seasonality, January, February, March, April, May, June, July, August, September, and OND. And you can clearly see the seasonality of this variability here during the summer monsoon season. The Somali jet, Somali current, and its instabilities, the Great World, the Socotra eddy, and so on are shown here. This region, the Seychelles Chagos thermocline dome that I mentioned before is critical for MJO and other monsoon related issues and intraseasonal variability here. There is also instability in OND here. This is just the seasonal waxing and waning of the trade winds and the associated barotropic and baroclinic instabilities and the tropical instability wave seasonality that shows up as residual or variance at interseasonal timescales, and you have similar instability wave response in the tropical Atlantic, which is obviously not as strong as the tropical Pacific, but has similar impacts in terms of coupled feedbacks at those timescales. There is some nice work done there by people like Hyore So from Utsol and so on. So this is interseasonal variability of SST at large scale, so greater than 10 degree latitude and longitude, obtained by computing for each quarter degree by quarter degree region the temporal standard deviation among the ensembles of spatially smoothed fields from the trim TMI data, again for seasonality. So you can see that large scale intraseasonal variability here now shows much more clearly the Seychelles Chagos thermocline ridge, low frequencies or large scale rectifications of the intraseasonal variability. This region is special because of the waves and the Indonesian through flow that's coming through here and interacting with the MJOs and other wind forcing in the gap, and this region is very specific for also collecting the MJO related coastal Kelvin waves interacting with the Indonesian through flow and creating barotropic and baroclinic instabilities depending on the season and so on. And there are also signals in the cold tongue region, the gap winds, Tehuana Peckers, and what's the other one I keep forgetting? You can look those up. Okay, so there's plenty of intraseasonal variability at small and large scales in the ocean that are internally generated and have the potential to feed back to the coupled interactions. This is the time latitude diagrams of the evolution of wind stress. This we are looking at 80 east, 90 east, so in the Indian Ocean sector, going from the southern hemisphere into the mouth of the Bay of Bengal. So there is a ITCZ region where a wind stress anomaly kicks up. This is at interseasonal timescales, and you can see the associated response in terms of the increased latent heat loss. So there is negative flux anomalies or interseasonal signal, and this is from an forced ocean model. So you can see the sea surface temperature cooling with a lag here. So the quadrature relation means the net heat flux has a large role to play, but you can see that there is also a mixed layer response which is spatially displaced from the peak of the wind stress. So the mixed layer response is much closer to the equator, and the increased wind speeds increase the entrainment, which it can explain the cooling as well, because remember the thermocline structure and entrainment of cold water, and there is no barrier layer, so the deepening of the mixed layer corresponds to the cooling of the sea surface temperature. But you can see the spatial displacement here and the time displacement there, because this is time being shown here. So these are the kinds of things one has to worry about: the ocean dynamics in terms of the local response to wind forcing, and oftentimes based on the scale and the spatial and temporal scales of the wind forcing, ocean also generates waves which get ahead of the forcing, and those are the waves that would hit the east coast, become coastal Kelvin waves, and go off into the Bay of Bengal and down towards Java and Lombok Strait, and that's where you get these kinds of intraseasonal signals as well, because of the wave interactions with the Indonesian through flow here, for example. Okay, so there are temporal scales, there are spatial scales of intraseasonal variability in the ocean, and they have impacts on air-sea interactions, and there is also feedback possible of the waves that are sent back westward. For example, the Indonesian through flow interactions with the MJO related Kelvin waves from the equatorial Indian Ocean create barotropic instabilities in the MJO season. That barotropic instability is released into Rossby waves which go westward, disperse towards the equator, and reach the SCTR, or the Seychelles-Chagos thermocline ridge, which is the region of MJO genesis. So that takes 12 to 24 months. Then we have to figure out the feedback from MJOs back to MJOs. So MJOs send Kelvin waves, generate instabilities in the southeast near the Indonesian through flow exit region, send the Rossby waves back. So there is a loop there. But what is the potential for feedback to MJO genesis? Will it be a positive feedback? Will it be a negative feedback? If it's a positive feedback between MJOs and these Rossby waves, MJO generated instabilities and Rossby waves, then how does the positive feedback get terminated, and so on. So that may explain some of the interannual variability of the MJOs. For example, ocean's role in feeding back to the MJOs on intraseasonal to lower frequencies and larger scales. Okay, so these are the kind of interesting things that ocean has to say about intraseasonal variabilities.